Hey guys, Greg here for another design tutorial. As I said last time, we're going to do the 5x5 because this is when you start getting tolerances and multiple layers of mechanism. So let's open the 3x3 tutorial that I've created earlier, and we're going to start off with that base, and we're going to go and make a 5x5 out of that 3x3. So first, save as 5x5. It's the first puzzle in the open recent list because I'm still exporting the video. I just filmed this maybe 10 minutes ago. So I'm doing the 5x5 now. The first thing we're going to want to do is go back all the way to the split function, because that's when we took the 3x3 mechanism and we split up the cube. So we're going to remove all the other functions from that design. For those who haven't seen the video, I highly recommend it. All of my videos are going to show a different aspect of design. If you want to know how to design a 5x5, you're still going to need to watch the other video. I will be putting timestamps in the description for the different steps of the design in every video, so don't worry, it's not because the video is 51 minutes long for the 3x3 that it's going to be long to watch. You can just skip to the different steps. Alright, so let's remove all those functions right there. I just need to keep the surface revolve function because that is how I split my solid. You'll notice that here I've got these two surfaces to cut the 3x3 that I showed on the previous video. I'm going to remove one of those, and I won't be needing the rest of the functions. I will keep the axis though, because I use that one to multiply the faces around the cube, and I'm going to do that on the 5x5 as well. So let's go inside the sketch of the 3x3. Now you'll notice something. Here is a basic 3x3 design. Now, in order to make a 5x5 design, I'm going to need to use VMech just, to make it more stable. Plus, it's a good thing because I'm going to show you how VMech works. So on a 3x3, you get this hook towards the inside. On a 3x3 with a V mechanism, you'll notice how there's first a hook towards the outside of the center, and then it hooks back inwards. So essentially, I'm going to need to add another circle around it, which is also for construction, by the way. I didn't say that in the previous video, but if you want an entity to not be used like this one in the surface revolve, you're going to need to make it for construction. So yeah, for some reason I can't drag this. Oh yeah, I fixed it. I put a fixing relation, so that means that I couldn't move it. Now, what I do is generally I put 2 millimeters between two circles. You can use the dimension here, the smart dimension, to click on both circles, and then you can use the dimension to give it 2 millimeters between two shells or two layers of mechanism. The diameter of 44 right here, we're not going to be using that anymore. Instead, we're going to make another circle that's tangent to the face right there. So by clicking on the line and the circle, we're going to add a tangent relation, and that way my circle is fully defined. When something is fully defined, it's going to be black. So again, for construction, and now I'm going to put a 2 millimeter distance between the top of the puzzle and the second layer of mechanism, I guess. Now, this little line here that's linking our mechanism to the outside, we're going to remove it because it's more of a constraint right now. And first, we're going to use this, this edge length, 60. Now we need to do 60 divided by 5, because it's a 5x5 times 2, because you put 2 layers here. And now we're going to go towards the inside, but we're going to stop here, and we're going to do a VMech. That means I'm going to put a hook towards the outside, not the inside this time. So again, using the arc, just like my previous video. And then I'm going to link the outside to the inside, and I'm going to make that line go through the origin. So here I click on the line, click on the origin, and press coincident. That's just so I have a conical mech. It could be anything, it could be vertical, but that would be, well, it doesn't change much, but when you make it go through the origin, you have this approximately the same thickness on the outside as on the inside. So for example, like a corner stalk isn't going to be shaped smaller towards the outside and huge near the mechanism, or opposite. It's just going to be like a straight stalk that goes straight towards the inside, and it's going to be of a relative constant thickness, which is what we're looking for. So for the V mechanism, again, we're going to use here about 3 to 5 millimeters. I'm going to put 4, just like last time. Last time I put 3, but this is a 5x5, so I want a little bit more mechanism just to make sure the parts are really stable in there. And then I'm going to add a dimension here, and let's say I'm going to put it at 3 millimeters, which leaves us with about 4.3 millimeters for the screw, and that's just the radius of the screw because it's going to be like symmetrical. So essentially you still have 9 millimeters to fit the screw, which is great because an M3 screw, even a head, goes through that shaft. So that's perfect. So we're going to leave it at that. This is the first portion. This is the first layer, like the 3x3 layer. This is the layer that's closest to the center. So technically this is like a 3x3 that is completely disproportional because you're going to have a thin layer and 2 larger outer layers. Let me just show you what I mean by that. Mirror and mirror that body. Okay, so here's your 3x3 with a small inner layer. Now let's go back in the sketch. Something that is interesting. Now here, putting a line that goes all the way to the axis isn't necessary in the sense that it creates big parts. I'm going to keep it now and show you later why it's not necessary. But okay, now we need to add the 5x5 layer. So we need to add an extra layer. Now that is very simple. It's much simpler than you think. For those who aren't familiar with designs, those who don't know how to design puzzles. Now we're going to do 60 divided by 5 because that is the width of a layer. And then we're going to go inwards towards the inside of the puzzle. Now there's something that's just a nice tip for you guys to have on a 3x3. Now if I put the mechanism like further than this line, then the edges would be cut off because you're essentially cutting through the center of the edge. This line goes straight through the edge, and if I had one cutting plane going all the way down here, well, the symmetrical cutting plane, the one here on that side, is gonna cut the edge off of the puzzle, which is not what we're looking for. Let me just show you here. If I do a mirror of that surface, here you see that the edge is cut off. Now, if I don't go all the way here and do a symmetry again around this line, then as you can see, the edge will have the mechanism portion right there. If I go all the way here, it's going to cut the edge off. Now the thing is, with a corner, it's even stricter. Here, in theory, you have an angle of 90 minus So okay, 90 minus 54.7356 103.17246. I know that one by heart because I always design puzzles. I just have to recite it in my head in French. So it's about 35.26, and you need to make sure. Actually, I think I made a mistake. It wasn't 90 minus 54, etc. It was actually just 54, etc. So 54.73. C'est 366. Oh, I put one extra number. It doesn't matter. So this is the angle you're looking for, 54.74. And you need to make sure that this line does not cross this line. Otherwise, the corner is going to be cut off. So let's bring it towards the center. Notice how when I make a line and click on that point and then go here, it's going to automatically show me like a dotted yellow line. Well, that line makes it so that your line right here goes already through the center, so it's already pre-constrained. There's already that relation between the line and the part that I usually do myself. Now, once that is done, we're actually not going to make this this point here fuse to that circle, because that means that we're not going to be able to fit the mechanism in. We're going to need to create a new layer of mechanism underneath the VMech. Again, 2 millimeters between the two circles is just fine. I'm a bit faster than my computer right now. It's having trouble following, even though I have like a GTX 1070. I don't even know why. Anyways, so let me just think. Okay, yeah. So now this little point here is going to need to be on that circle. Okay, that's very important. But here, you want to make sure that this is underneath the top face. Otherwise, if we go too high, it's going to cause oozing. I'm going to show you all that in a minute. Now, I just noticed something. I'm quite close to that that line right there, and that's not something I really like. So what I'm going to do is I'm going to reduce the size of this segment to 1 millimeter, and here I'm not going to make this line go through the center. Instead, I'm going to make it go a little bit like that. That way the corner stalk, which is the space between this line and this line, is slightly thicker. So now that's done, I can just create a mechanism, so just an arc, which is going to link that line to this line. And dimension that, let's say I want a corner stalk thickness of 4 millimeters, so I just put like 2, and 2 will be fine. This is essentially half of the corner stalk. Well, it's not exactly half. Let's just put 2.5, because it's like a triangle, and here you're seeing the 2.5 you're seeing is the distance between the center of the corner stalk and the cutting plane. So technically this is going to be a thickness of about, I don't know, like 4 millimeters or something. That's approximate. And now this line, by the way, I'm not going to use that one. It's for construction as well. So here you've created another line. So here you've got your 3x3 going all the way here, and here you've got an extra cut going all the way here. And now if you notice, that means like this part here, this little part that you see here, is going to be an inner layer of the 5x5, and you see the hook that goes inwards, and for the outer layer you have another hook going inwards, and that's going to be like your 3x3 section, so the outer layer of the 5x5. So now if we revolve this around this axis, you'll notice I have these two surfaces. I'm going to make the body transparent, just like in the last video, and you see this is my cutting plane. You see the two surfaces are obviously revolutions, because we want the puzzle to turn. Now we're going to mirror those, so I still have my mirror function from before. I'm going to mirror both surfaces, and now I've got this. And once that's done, I'm going to use the axis from the last video, and I'm going to create a circular pattern of all those cutting planes, and I'm going to copy them threefold around the axis. And there we go. Now that that's done, you'll notice I've got my 5x5 mechanism, and just the thing I was talking about, you know, the corner stalk, you can see here, like if you can reach the inside of the puzzle, that means your corner is still in place. Now, the thing is, I explained earlier that the closer you get to that line, the smaller the corner stalk is, because if you go further than that line, you're essentially cutting it off. I'm going to show you, if I get really close to that line, you'll notice how my corner stalk is going to be extremely thin. This is the space for the corner stalk. So that's why I was saying that. So you need to make sure you've got a little bit of leeway there. So yeah, again, at least, I guess, you know, like 2 millimeters is fine. It would be enough. So make sure between the axis and the point you've got 2 millimeters. On some puzzles, I tend to go down all the way to 1. That's when there are a lot of parts and the puzzle is complex. I'll probably need to do that in one of my future videos, but for now I'm going to stick to simple stuff. So now, it looks complicated from here, but don't worry, it's not that complicated once you understand the 2D aspects of how a puzzle works. So essentially the cut view of the surface. So if I do like a section view, you're gonna see my solid right there, and this is how you're gonna cut it. I can't let my click go because otherwise you're not going to see the lines, but here you've got the VMAC right where my cursor is, and here you've got here you've got the first layer, and here you got the outer layer, and you can recognize the mechanism. This is like a VMAC edge right there, and you can recognize it if you've already opened a 5x5. You'll see that this is how it works. So it's actually quite easy. You just have to add one layer right there, as I showed in the sketch. So now we're going to cut it open. That's the fun part. So I'm going to split this solid with all the surfaces I've created, like that. And now I'm going to press cut bodies. Now I've got a tiny software that was created by a member of the Twisty Puzzles forum, and it's somewhere in there. It's called Split Helper. So I'm going to use that. It basically checks all the boxes for me. Right now I have 99 boxes. That's the number of parts in a 5x5. So I'm going to press 99 and click go. So it's going to check all my boxes for me, and that is like, oh, that is such a relief. I hate clicking on those boxes. Once when I started Twisty Puzzle Design, I had to click on 1,670 boxes by hand, just like myself. So it's that was a pretty long process, and I am so glad that somebody created Split Helper. Anyways, same as before, we're going to isolate all the unique pieces. Now you'll notice that on the 5x5 there are, okay, no, it would be more on 7x7, but if a piece is symmetrical, let's say imagine this one and this one were two different unique pieces that were symmetrical, well, you would only need one of them, because then you can do a symmetry using the symmetry function, the mirror function. So we're going to keep one of each unique piece, like that. And as you can see, we've got the same problem as yesterday, where the centers are so long, and they don't need to be that long, and we need space for the core. You see, this center stalk is extremely long. Now this is where I was saying you could do, you could improve on the design. So here, instead of going all the way down to the center with that line, what we're going to do is we're going to go all the way to another circle, which is also going to be 2 millimeters apart from the previous circle. And all right, let me just do that, because I'm speaking faster than I can design because my computer is slow. I think it's slow because I'm exporting the video right now, but yeah, I guess I can still explain anyways. And now that I've created this line, again, previously it was all the way down to the axis, so we need to link it to the axis, but we can do this through that circle right there by creating a new arc. So right now what we're doing is essentially making a spherical core. And I'm going to show you that right now. I'm not sure the split function is going to follow. Normally it should. Yep. So now your centers, they look like this. It's as if they were positioned on a ball core. This is what your center looks like. It's like a section of a ball. Well, the opposite of a ball. It's just like concave. And here is your spherical core. And that's what it looks like. So it's actually a very nice method. For some reason, this center is fused to the core, which means that my split function had a small bug. So I'm going to fix that one real quick. That means I just need to check a few boxes that were unchecked by the failure of the part recognition in the split function by SolidWorks. So let's go down there and see which one. Oh, there it is. Number 86. And number 97. So there were only a little bit of, only a few problems, just a small bug. So that happens. And in this case, we're also going to hide the core. And now I've hidden all the unique pieces. So now I'm going to select them in my tree, like that. And I'm going to press delete. And now I can delete or keep bodies. I'm going to press keep bodies. And I'm going to delete them. Delete the rest. And now if I show all the bodies, you can see that the only bodies left are my center, my 3x3 edge, 3x3 corner, the wing piece between the edge and the corner, the central corner, and the central edge. So this is all you have in a 5x5. Now we're gonna hide the parts that don't need tolerancing. The only ones that need, well, I'm gonna undo that. The only parts that need tolerancing are the parts where you have an interface here that would be squeezed between two sides of the same part. So here, for example, the blue lines that I just highlighted, this one and this one, well, these are essentially this part of the center that's being squished by this piece, and you need to avoid that at all costs. Now, what's important is that this surface here is the one that keeps that part in place. And this one, this surface, doesn't really need to be in contact because this part is held in by the surface underneath. So you actually need to put a 0.5 millimeter tolerance on the top of V mechanisms. I always use 0.5. Technically, you could use any number between 0 and 2 because, well, it's 2 millimeters thick. You can't go higher than 2. But you can essentially put as much tolerances as you want. It just needs to be enough for it to be smooth. But since you don't need contact, it could be like a 3 meter tolerance if it was a big design. But anyways, on the 33 by 33, for example, I happen to use over 2 millimeters of tolerances on one of the VMechs, the one at the bottom, like the 3 by 3 VMech. So it's a lot, and it was just enough. So on any puzzle like this one, you could use 0.5, and that's more than enough. So we're going to start with the tolerances by clicking Surface Move, and I'm selecting the top face of my VMech, like that. Flip direction, and I'm going to remove 0.5 millimeters. As you can see here, this is the current thickness, and this is the new thickness. Now I'm going to exit the isolate function. Here I've got another part with VMech. You see VMech on the two sides, so I'm going to select the two faces, press face move, and offset those by 0.5 as well. And then I've got this edge here, and I'm going to click the two VMech faces and offset those. Now, I don't know if you guys remember from the last video, but I said there was a small issue with SolidWorks. If we look at this piece, we notice here that we have an interface between two edges here, one that's on a bottom surface and one that's on a top surface. SolidWorks has a little bit of trouble recognizing that, so we're going to do a move face, and we're going to move that face by almost nothing, 0.001 millimeters. Sorry if my voice is shaking. It's really cold down here in my house. I don't know why. I think it's like 18 degrees. And I didn't use my my microwavable slippers this time, so yeah, it's getting cold. Anyways, let's see what's left. Well, I've used the VMech on these three parts, so now they're offset. As you can see, here's my tolerance right there. You can see it. That's where there's no material anymore. And there is one last one that you need to absolutely not forget, and that is the core. Because if the core is like this, those parts won't be adjustable because they'll be stuck between the center and the core, and therefore, if you want to make it tighter, you're just going to squeeze them against the core, which is absolutely critical. So now I'm going to click on all the faces of the core, and I'm going to do that same tolerancing function, which is the move face function. And again, I'm going to flip the direction, and now I've got the sphere in the core, the spherical core that's been pulled back 0.5 on the outside. So now I have a little bit of leeway between the center and the core. All right, so now I need to do fillets. And well, I've already done that in the previous video. And you know what, I am gonna do that step, but technically once I've done this, you can do the rest yourself. Because the thing is, everything that I explained in the previous video is enough to complete this puzzle as is. So technically right now, I'm done with the explanation, because you should know how to do this if you've seen the previous video. So if you want to know how to do the rest, watch the previous video. When it comes to me, I'm gonna try to speed design this this 5x5 and end the design just for fun, because you know, why not? So yeah, let's. I am gonna talk about what I'm doing though. That way it stays interesting. So let's do this. So I'm gonna fillet those functional edges, but I am gonna increase the fillet size, but not too much, otherwise the quarter stock is going to be too thin, so I need to make sure it's not too thin. I've put 1.5 millimeters radius. Now I'm going to use 1 millimeter on the outside because I think it looks good. And now there is one thing that I can do on this piece that I couldn't do on the other puzzle. I can make huge fillets on the inner 3x3 because, well, the piece itself is gigantic. So I'm going to put 8 millimeter fillets. That's huge, but it's gonna make better quarter turns, I guess, quarter cuts, sorry. And then now I can use 0.7 millimeter fillets for the top and bottom surfaces so that they don't catch with upper layers of mechanism. And now the corner is done, so I'm gonna hollow that out just like the previous one and hollow it out at 0.8. All right. Now that that's done, I can move on to the next piece. Now, for those who want to know how to make a hole inside the core, you know, for finalizing the core, I'm going to show you that later on. Oh, do stay tuned for the core design, because the core is very important. There is something that you can do to make sure that there are no stacking problems, because sometimes with part stackers, the core has a little bit of a problem, which is the fact that it's hollow. And when it's hollow, some parts can actually be stacked inside the core without you knowing, and therefore when you receive the puzzle, there are parts that are missing, and that is a big problem. So yeah, just don't forget to check out the core design, because that is extremely important. All right, I'm going to continue designing that part in the meantime. So right now I'm doing the wing piece between, I don't know why I call it that, but I've always called it that. So no, okay, I clicked on a function that automatically selected certain edges. And that is not what I wanted. It almost selected all the edges of the model. So yeah, now I've done my 1.5 millimeter fillets. I need to do the outside, the appearance, which is 1 millimeter. And this is what it looks like. Here I've got my quarter cut fillets. These are important because this is where the piece is gonna interact with other pieces of different layers, and I need to make sure this is big enough. 1.5 is enough, you know, it's still gonna be good. So I'm actually doing a design that I know I won't print, even though it's like not exactly useful right now, but whatever. It's fun to design this with you guys. All right, so let's shell this at 0.8 millimeters. Now it's hollow, and I can quit the isolate function. Now you'll notice I've done the corner and the wing part. I can do the bigger edge. I am going to show you a small function, an extra function here. It's just a tip. I might have a few tips and tricks as I go. It's not guaranteed because I don't really think of them in advance. It's just that when I reach that point, I'm just going to realize that I can do things better. So 1 millimeter again. Okay, now I've got some more corner cutting fillets to do. So those are the lateral edges, those that are going to interact with the rest of the puzzle. I'm going to put 2 millimeters here. It just sounds like a good idea to put bigger fillets right there. And once that is done, well, you know what? I can show you that function I was talking about. Let's remove those 4 fillets. So you see here, like if I click on one edge, here it's going to offer me multiple functions here. If I select this one, I notice that it's going to automatically select the pink edge. And if I select this one, it's going to select way too many, so I can always click on that, and it just selected this edge automatically. I can do it again here. See, this edge was selected automatically. Anyways, that's just an extra method that you can know that is quite useful. Here, if I select this edge, for example, all that's left are 0.7 millimeter edges, so I can take all the convex edges, and it's going to select everything. And now it's going to finish filleting my piece if I put 0.7 millimeters. And you can see I just selected one edge and it finished the whole part for me. So it's just like simplified design, which is really cool, because if I had to click on every single edge, every single design, it would be a lot of work. So I'm glad that there are these tiny like SolidWorks shortcuts for me. It's really useful, and it's great. It's a really good method to design, because that way you gain time, which is really important. Now, 1.5 millimeter fillets. I'm doing the same as before. I'm creating those well, you know, not just appearance, but corner cutting fillets right now. Something that's very important as well, I keep saying that, here, you can't, like when there's an interface of 4 edges, you can't just select 3 and fillet those. It's not going to work. So always select them all. And even if it looks like it's not working, like when you click on that edge, it doesn't render anymore, it doesn't mean it's not going to work later on. So don't hesitate to check out, once you've selected everything that you want to select, check out if it works. Now I've selected all my corner cutting fillets, put them at 1.5. I'm going to put another appearance fillet on the top face at 1 millimeter like I always do. And finally add 0.7 millimeter fillets on the inside, right there. And again, I can select the function that selects all convex edges, and it's going to do the work for me, and I just have to press enter or click OK. And now I can do the hollowing of that part. Show that thing at 0.8. Alright, I think I'm going to be finished before the 3x3 video finishes rendering, which is quite cool. That way I can just prepare that video as well and edit both at the same time. That's going to be fun. By the way, in one of my previous videos, I've had a small issue where I was stickering a puzzle and the sequence wasn't accelerated when it should have been. The thing is, I've given a bit of those videos to edit to my roommate. She's a student, and I'm essentially helping her pay rent by giving her a bit of editing work. But it doesn't seem to be working out, so I'm going to edit the videos myself again from now on, because I don't want any mistakes. I want good videos and high-quality videos for you guys. So yeah, even though I tend to be lenient, it wasn't the first mistake, and there were quite a few mistakes made on my videos, so I'm going to take over again. Anyways, let's click on that and make an appearance fillet. Now, something that's quite peculiar is here, the fillet was too big, and that created a sort of oozing right there, as you can see. It's barely visible, so I can leave it, but I still don't want oozing on that 5x5, so instead of leaving the oozing, I'm going to reduce the appearance fillets down to 0.7. That means I can do all my fillets like that. So I'm selecting all my convex edges, 46 edges in total, so it's going to select them by itself, and press enter, and now the part is filleted, so that's perfect. Now I add a shell function, press that, select the part, press enter, and it's going to shell itself, so that's perfect. SolidWorks is a really good software for that. Like, you barely have any work. It has a lot of useful functions that can save you a lot of time, which is why I really like using it. Alright, let's do some corner cutting fillets again. 1.5 everywhere. Boom, right there. Here I'm going to select connected to start virtual loop. That's going to select the 2 last corners, and here if I select this edge, it's going to select all 4, and that is perfect. I just have to press enter, add a 1 millimeter fillet for the appearance on the top face, I should have waited though that the video was finished editing before starting this video, because it is lagging quite a lot compared to what I usually have. I'm usually much faster at this than I am right now. Alright, so now we've finished the centerpiece. Now, it goes without saying that the core doesn't need to be rounded, considering it's a spherical core. So now we're gonna prepare the screws. First, we need to make a center cap. So that was just like last time. I'm gonna take a plane that goes straight through the center, create an axis going right there, and create a plane to cut that cap off. And now surface revolve and create that cutting surface right there, which I'm gonna split the center with in the features split function. And I'm going to select, that center and cut it using the surface revolve. It's going to be split into two parts. Check them, click OK, and now we're good. Now I'm going to isolate that cap right there. I should do like a speed designing challenge, like try to speed design the 3x3 and see how little time it takes me. I'm curious just to see the result, like do an average of 5 or something. I think it would be fun. Anyways, let's do 10 millimeters here, 10 millimeters there. I'm just doing like an equal relation, which means the two lines are the same length. Let's just take it down to 9.5 or 9. 9 is good. Yeah, I don't want it to be too close to the edge, otherwise the centerpiece is going to be too thin. Now that that's done, I can just select those 4 lines and offset them like this. With the offset entities function, offset it by 1 millimeter, like this, perfect. And extrude that to make a cap, 2 millimeter cap. All right, now we're good. Now, I have an idea for right now we're gonna create like the reverse cap, so the female cap in the center, and I'm gonna show you a method. Like if I select, I just created the sketch on that plane because it's essentially the same plane as where the reverse cap is, and if I select these edges here and do an offset directly from these edges and offset it by 0.1 millimeters, I won't have to add the tolerances later on. It's just like my sketch is already there, so I just have to remove that sketch from the center, and that's good. So now that I've done the cap, I can hide the cap, and I've got my sketch here, which is offset by 0.1, and that means I already have the tolerances. So when I'm gonna cut the cap, like the female cap in there, I'm just gonna have to remove 2.5 millimeters of that square that I just created that is slightly offset, and the tolerances are already done, so that's perfect. Now that that's done, there's only a few things left, and that's cutting up the hole for the screw head, which is going to be 8 millimeters wide, which is just fine. And now I'm going to extrude that by about 2 millimeters. Although here, I don't know if you can see here, but the screw head is way too close to the outside, which means the part is going to be very thin. That's something I don't want. So I'm going to press OK just so that the function is done. But I'm going to go back into the sketch and edit that sketch to make it slightly smaller. As I said, the screw head of an M3 screw is between it's technically 7 millimeters, and I can put 7. I put 8 just to have a little bit of leeway, but 7 is fine, and I'm just going to leave 7 because here I don't want it to be too thin on the side. Okay, so if I select this face right there, this surface, sorry, and we look at the cross section right here, we're going to see that this is not too thin right here. We could technically even look through the part. As you can see, this here is a relatively sturdy geometry because it's quite thick. So that's just what we need. Now we need to do the hole for the screw itself, not just the head. Just like last time, it's going to be 3.5 millimeters so that the diameter of 3 goes straight through it. But so that it's not large enough for the screw head to go through, obviously. and we're going to do up to next. So in the direction, instead of giving it a value of, of digging, instead of digging by like 10 millimeters or 2.5, we're going to do up to next, and that means it's going to stop cutting through the part when it reaches the next surface, which is technically the end of the centerpiece. If I did blind, which means giving it a value, then it would also, there would be a chance for it to cut through the core, and I want to take care of the core separately. So I'm going to do up to next, and now I'm going to do a new sketch in the center. Well, no, first I'm going to hollow out the center if I can. Usually centers are a bit of a problem to hollow. I think there's going to be a problem. Yeah, see, it's bugging right now, so it's not going to work. So I'm just going to leave this part out. I'm going to leave it full and not hollow. So now I'm creating a sketch on that surface because that's the only flat surface I know that is perpendicular to the direction of the screw. I can't do a sketch on the core this time because the core is spherical, and you can't just draw a 2D drawing on a 3D surface. And I'm going to make it 2.7 millimeters wide, just like last time. And now I'm going to extrude this all the way down into the core this time. So I'm going to use a blind direction. And I'm going to give it a distance of 15 millimeters. That should do the trick. Yep, we're good. And just like in the previous design, I'm first going to make a symmetry of that thing, of that hole that I created, so that it's also on the other side. So I'm going to mirror that, mirror a function, a feature, sorry. Click on the feature and mirror that feature so that you have a hole on the bottom. And I'm going to use the original axis that I used in the previous video to revolve that and make 3 copies around that axis of the feature. And that way, I will have a core. And that's wonderful. Which means now I've got my fully prepared design with all the parts, but I haven't hollowed out the core. So I'm going to hide all those parts, and I'm going to work on the core. That's very important. Yeah, I said important again, but it is extremely important. So I'm going to shell this core. But the thing is, as I said earlier in the video, if you saw that section, because you're probably skipping through sections, I said that when you hollow out the core and then you use part stacker to stack parts, sometimes some parts finish inside the core because there's free space, and the software considers it to be free space. And so when you receive the core, you can't get the parts out because they're just hiding inside the core. So there is something that you can do, which is quite cool because it even makes your core sturdier, and that's great. Now, I've just made my core hollow, and see on the inside, this is what it looks like. And the parts could be stacked inside. Now, you don't want that. So what you're going to do is you're going to create a solid that is bigger than that core. Any solid. Here I'm just going to make a cylinder because it's easy to make. And I'm going to make it big. Bigger than the core. Let's say 20 millimeters in one direction, no, 25, and 25 in the other direction. So now I don't want to merge it though, because I don't want to have my core transformed into a cylinder. That would be pretty stupid. And now that that's done, I'm going to hide my cylinder, and I'm going to copy the core. Whoops, not the cylinder. I want the core. I can also select the core here, shell 7. And I'm going to press copy. It's going to say you have like no rotation or translation specified. Do you want to proceed? Yes, because I just want to make a single copy that doesn't move. I want it to be there. So now I'm going to hide the original copy. That way I save my core, and I'm going to work using my copy of the core. Now in the features, I'm going to do combine, and then I'm going to do subtract. I'm going to select my cylinder, which is bigger than the core, and then I'm going to select my core and press OK. It's going to create... Oh wait, it deselected the main body, so I have to select it again. I press OK, and now it's going to say, which bodies do you want to keep? There are 2 bodies, the outside and the inside, because I've just subtracted the core from that body. The only one that I'm interested in right now is the inside. So I press keep the inside, OK. Now this is what you find inside my core. here is, let me show you the core. Now this is the core. This body right there is the core. This one, I'm gonna try to select the face. Yeah, the face that you see here is the core, and this is what you see inside the core. So if I hide the core, this is what's left. And that's essentially a negative image of the space you have in the core. So what I'm gonna do is, now that I have that negative image, I'm gonna take any plane and go perpendicular to that one. And I'm gonna draw tiny triangles. Now, it's gonna be difficult to explain why. You're gonna understand as soon as you see the result. So I'm gonna do that really quickly. I'm gonna do, okay, 4mm triangle right there. 4mm to an edge, it's gonna be an isosceles triangle. So this is the same length as this. And I'm gonna do that again on the opposite side. And here, I want all these edges to be the same length. And I'm going to do like a 1mm gap between the triangles. This is going to be the thickness of the inside of the core. I'm just going to explain it in 2 seconds. Technically, this is not 4 that I want. I want 4 between this and this. And now that I have that, I want 4 between this and here as well. Okay, so now I have 4mm between this and that. 4mm between these two, and 1mm between these two. So what I can do is now copy those entities by 5mm in one direction, like this. Make, let's say, 10 copies, and then same in the other direction. And I'm gonna make 10 copies spaced by 5mm. Now, you're probably asking yourself, why 5? Well, that's because here I have 1mm as well as here. So I have a constant thickness in there. My throat is getting kind of dry. Anyways, I have a constant thickness now. So I have this grid of tiny triangles, and now using that whole sketch, so I'm leaving the sketch right now, using that whole sketch, I'm gonna press cut, extrude, and I'm gonna remove all those triangles from the core. Now the reason why I did that is so that the final result looks like this. I've removed triangular segments from the core, and all you see is the inside of the core with this structure that's going to make it very strong, and it's still going to be hollowed out, but there won't be enough space in those tiny triangles for other parts. So the stacking software is going to understand that your core is filled, and therefore it's not going to try to stack other parts in there. So now I do combine, and I combine the core that I had with the inside of the core that I created and press OK. And now if we take a look inside what I just created, this is what my core looks like. So you've got the regular core holes where you screw the parts in. You've got one here on the inside as well. And you've got that very strong structure here. And that's going to make the core indestructible, and the parts are not going to go and hide themselves in there when you stack them, which is what you want to avoid. And now there's one final thing that I forgot to do. Technically, I should have done the shell after that. Well, you know what? I'm going to go backwards to I'm going to roll back to before the shell, and I'm going to do that. So features, chamfer. I forgot to add the chamfers, the 0.5mm chamfers here on the screw holes to make it easier to insert the screws. I'm going to do 0.5 times 3, 0.5 times 60 in that direction. Perfect. Click on all the screw holes. Bam. Got them. And now the screws will be easier to insert. And now that that's done, I can just roll forward, and that's gonna redo everything that I just undid, but with the chamfer that I created. So that's just an easy way to intersect, to add a function before another function. It's like editing, but then going backwards and forwards again. So now we've done that. Every single part is ready to print, and all you need to do is save all the different files as, well, in this case, I do have to admit there's something that I didn't show in the previous video. Last time I stacked the 3x3 parts I didn't show you how to use part stacker, so I'm going to show you that now. You see here, I've got my individual parts, so I'm going to press Features, Delete, and I'm going to select one and delete it. Then I'm going to select the other one, delete it, and do that for all the bodies. I'm doing this fast, so I'm not really... Okay, so here I've deleted all those bodies right there. So I'm going to undo the deletion of that one, and I'm going to save it as an STL file. So the reason why I do this is because I want there to be only one body at a time when I'm saving the document. I'm just going to save it right now as SolidWorks document. Now save as, and you go to STL. And now let's create an STL folder for the 5x5. All right, so now you press, before you press save, you're going to need to give it a name. Now this part needs to be copied 12 times because there are 12 3x3 edges in a 5x5. So let's call it 12, because the thing is, the part stacker is going to recognize in the name how many parts of each type you will need by looking at how the name ends. In this case, the name ends with 12, so it's going to copy it 12 times. So now I'm going to undelete the second part and save it as 24, because I need 24 copies of that one. So 24. Then I have to do this for every single part. The corner needs to be called 8, because obviously there are 8 corners in a cube. So 8. And I'm going to explain, like, if you have the same number of parts. Okay, here, this one needs to be copied 24 times, but we already have a file called 24, so we're going to call that A.24. It actually takes into account only the digits after the last dot, so 8.24 is going to work. And then you can just do B24, C24, etc. So this is going to be B24. Okay, B24. All right, then undo, redo. Oh, I know why it's not lagging anymore. The video finished exporting, so that's why. Now I can go fast. Now there's the center cap. It's going to be called 6. Then I'm going to undo the deletion. Okay, this is going to be called 1. All right. Now, the next one is the center, if I'm not mistaken, and this is going to be called A6 because I already have the center cap called 6, and now we're good. Okay, so I've exported all my files. They are located somewhere in there. Let's go and see. So, complete designs, SLS, nope, not there. Tutorials, 5x5 STL, and here are all my files. Now, the SolidWorks document, we're not going to need it anymore. I could use it to show you how to make templates, but I want to make a separate video from that to make the sticker template. So I'm going to just save. You know what? I'm going to undo all of that because it looks better when I have all the unique parts. I'm going to save it as that and quit that and leave the design. Now, all that's left is to stack those parts. So I'm going to show you now how to use part stacker. So it's in softwares, so logiciel, all right, part stacker new. And now I have to import all those parts. Let's copy the destination folder. And as you can see, name 1, quantity 1, name 6, quantity 6, name 24, quantity 24. It actually detected the number of parts of each type that I wanted. Now, the minimum clearance between parts, I put 0.8, but that's just me. I don't generate a center box. I prefer generating it using Materialize, which I'm going to open as we speak. And the bounding box, let's just put like 80 millimeters and see if that's good enough. This is quite random, actually. The bounding box is very arbitrary. You need to pick something that you know the parts will fit in, but you don't want it to be too big because it's going to stack them inside that bounding box. So if you have too little parts and too big a bounding box, it's only going to use part of the space and it's not going to optimize it into a perfect cube. So it's very important not to have a too big bounding box. All right, so it's still preparing the, well, it's still meshing the parts right there, because each STL part is actually decomposed into a set of micro cubes, and it's going to use those to see if parts are intersecting, just to make sure that all the parts are separate inside the final STL assembly file. So that's actually very well optimized software. I think it was really well designed. It was made by Tom van der Zanten, which is the name of a very good puzzle designer as well. He created some pretty impressive designs. He was the inventor of the curvy copter. So yeah, he used to make a lot of designs. It was really great. So it's too bad he kind of stopped making those. Okay, as you can see, the bounding box is a bit too big. You can recognize the cube here, the square, and the square on that side. So I'm going to stop right now, otherwise it's going to take too long to stack. I'm going to move it up to 100 on each axis, and I'm going to start again. And here I'm going to prepare my scene, which is a printer scene on Magix, and I'm going to use that to add a center box to the parts once they are fully stacked. So let's just see if the new parameters are a-okay for this assembly, this stacking. Most of the time you have to try 3-4 times to get them right, to get the size right in the part stacker, so it's kind of tedious. It's too bad that it doesn't calculate the bounding box size, but you know, that would be a lot of work to code, so I'm not surprised it was made that way. Plus, it's already making us save a huge amount of time, so I'm just thrilled that it exists. So let's see. We're almost done. I think it's meshing the core right now because the core is so complex the way I designed it. But you know, it's something we call in French un mal pour un bien, which means like something negative for a positive outcome, because now it's stacking parts and it's not going to stack any in the core. Okay, as you can see, I made the bounding box too big, so now there's this whole section of parts missing. So the volume is not optimized at all. Anyways, you have to try this a few times, and then once you see that it's cubic and well made, you can export the result as STL. I'm just going to do it now, even though it's not optimized at all, and call it 5x5. And now that that's done, I'm going to import that file. Where did I do it? Right, there it is. Tutorials, 5x5, and right there. And as you can see, clearly not optimized, but whatever. Let's just do a center box around it. I've already done that previously. I just wanted to show part stacker. I'm just gonna show you the center box again. Let's call it 5x5 and finish. And I just want to show you why it's not optimized. As you can see here, it fits nicely inside a box, but there's that whole section of parts missing. The reason why it's important to create a box on Part Stacker and optimize the size of the box for the parts to go in there nicely is because it's going to make printing cheaper, because most services calculate the price using the bounding box volume. So it's very, very nice to have a software that can do it for you and make a nice cubic assembly of your parts. Alright, now that that's done, I can just save it as. I call it generally WSB, which means with center box, and we're good. So now I've finished my 5x5 design and it's ready to print, and I will make another tutorial for the stickers. So for now, I'm gonna leave it at that. I hope you guys liked the video, and I will see you guys in the next tutorial.